Hello everyone, hopefully you have your notes in front of you and you're ready to take a few notes on how to do a two-sample t-test and t-interval for proportions. So here we go. Let me see if I can get this started. Alright, so here's the situation. A community hospital, the burn unit, can you get that out of the way? The burn center is experimenting with a new plasma compress treatment. A random sample of 316 patients with minor burns received the plasma compress treatment, and of these patients it was found that 259 had no visible scars after treatment. Another random sample of 419 patients with minor burns received no plasma compress treatment. For this group, it was found that 94 had no visible scars after treatment. So the question that we're being asked to determine is the plasma compress treatment more effective than the standard treatment? And so you can see why this is a proportion problem, because we're talking about what proportion of the patients had visible scars after treatment. Here's the assumptions when we're setting this up. So our assumptions are, since we have two separate simple random samples, we need two independent simple random samples from populations or from randomly assigned treatments in the event of an experiment. Notice the similarity between this and the two-sample t-tests that we did in Chapter 11. The populations, meaning both populations, since there's two of them, have to be at least 10 times the sample. And you have to be able to use a normal approximation for both populations. So that means you need to test the first sample, n times p, and also the second sample, n times p, and all of them need to be greater than 10. Now, you can, in some cases, get away with NP being greater than or equal to 5, and in some textbooks and in some cases, 5 is acceptable, and we'll be talking more about that in class later on in this chapter. The formula for a confidence interval, in this case, is the statistic is given by p hat 1 minus p hat 2 plus or minus the critical value, which is going to be the z star, and the standard deviation of the statistic, which is given by the standard deviation of the two p hats. All right, that should look very familiar to you. It's very similar to the one sample z proportion, except it's just got now two of them and we're subtracting them. Now, we don't know p, we don't know rho, so we can use p hat as an estimator if we don't know p, if we don't know the population, if we don't know rho, the population parameter. This form, the part underneath the square root symbol, is called the standard error in this case. If we're dealing with two proportions, then the standard error is the part underneath the square root. When you tack on the z star part, then it becomes the margin of error. So back to our situation, if you remember this question, what is the shape and standard error of the sampling distribution for these different proportions of people with visible scars between the two groups? So first we have to check normality. Since N1 P1 is 259 and N2 times 1 minus P2 is 325, and then we check the other one as well, and they're all greater than or equal to 10, we're able to say that the distribution of the difference in proportions is approximately normal. We had to check all four. Then we can plug in our different percentages, and we can calculate our standard error using the formula that I just showed you. So the standard error then is 0.0296. Next question up is, what is a 95% confidence interval for the difference in the proportion of people? So we test our assumptions. We have two independent, randomly assigned treatment groups. Both distributions are approximately normal because we check all the different proportions, and they're all greater than or equal to 10. Since there are 735 total people in both of our samples, then we have to assume that the population of burn patients is at least 7,350. Right, so we add them all together. And then we can calculate using a z star. We're doing a 95%, so z star is 1.96. And we can plug those in and we get our answer. So we can say that we're 95% confident that the true difference in proportion of people who had no visible scars between the plasma compress treatment and the control group is between 53.7% and 65.4%. Okay, let's go to another example. Suppose that researchers want to estimate the difference in proportion of people who are against the death penalty in Texas and in California. The two sample sizes are the same. What size sample would be needed to be within 2% of the true difference at a 90% confidence interval? Well, we want to be within 2%. That's our margin of error. So we say 2% for our margin of error. 90% confidence. We look up 90% confidence, a 90% z-score in the test booklet, and that equals out to 1.645. We're going to assume, for the purposes of this, that it's 50%. And that's pretty standard when we're trying to estimate a difference in proportions. If we don't know what the actual proportion is, and we're just trying to estimate it, the best estimate is that they are both 50%. That's called a conservative estimate. If you go with a bigger estimate, then you start being more specific, and we don't want to do that if we're just trying to estimate. So anytime we're trying to estimate, we're going to use 50% as our estimate. So we plug in 0.50% for p hat 1 and also 50% for p hat 2, and then we plug them in, and we can calculate. Since they're the same, we can add those two together. Take the square of both sides. Okay, so let's try this. Keep going. And you can solve that algebraically, and you get 3,383. So that's a very conservative number, but it should work. And if the proportions are truly not 50%, then that will be discovered if our sample size is that big. Okay, example 3. Move that out of the way. A forest in Oregon has an infestation of spruce moths. In an effort to control the moth, one area has been regularly sprayed from airplanes. In this area, a random sample of 495 spruce trees show that 81 had been killed by the moths. A second nearby area received no treatment, and in this area, a random sample of 518 spruce trees showed that 82 had been killed by the moth. Do these data indicate that the proportion of spruce trees killed by the moth is different for these areas? So notice that if we're not being asked for confidence interval in this case, we're actually being asked, does the data indicate that the proportion is different? So that hopefully by this point in stat class should sound like a hypothesis test to you. So we're going to have to make an hypothesis test. So it's a two-sample hypothesis test, exactly the same way we do a two-sample mean test. The null would be that the two proportions are the same. So we can write P1 equals P2, or P1 minus P2 equals 0. The alternate, we have a couple of different options. P1 minus P2 is greater than 0, or P1 is greater than P2. We could do P1 minus P2 is less than 0, or P1 is less than P2. Or a third option, P1 minus P2 does not equal 0, meaning they're different, or we can write it out that way. Make sure, just like with the means, that you define both of them. You always have to make sure that you define everything. Now, since we're assuming that the population portions are equal in the null hypothesis, remember back to our null hypothesis, we're assuming that the proportions are the same, P1 equals P2. That would mean that the variance are equal, and therefore we can pool. When we're doing mean testing, we never pool, but when we're doing proportion testing, we will pool. So what's going to wind up happening is we're going to combine our two samples, and we're going to get one big overall p hat. So you take the number of trees killed in both different samples and you add those together over the total number of both samples, and you wind up getting one global p hat that we're going to use for our standard error calculation. So the formula for hypothesis test, z, we're doing a proportion test, so it's going to be a z-score, is going to be the statistic p hat 1 minus p hat 2 minus the parameter, and usually the parameter part is 0, just like when we did two-sample t-tests, divided by, now notice the difference, pay close attention to the difference between these two. Right, this is an individual sample for p hat 1, and this is the individual sample for p hat 2, but underneath we're using the global p hat, where we combine the two p hats, we pool them. So we actually wind up having 3 separate proportions that we're using for this problem. And as I said, usually this is your population parameter. Usually we're saying P1 is equal to P2 or rho 1 is equal to rho 2, and that would be 0 in that case. So back to our example, and you have this written down. The question is, does the data indicate that the proportion of spruce trees is different for these 2 areas? We have 2 independent simple random samples of spruce trees. Both distributions are approximately normal because we tested all 4 of our NP statements, and they're all greater than 10. We have to assume that the population of spruce trees is at least over 10,130. It's a fairly safe assumption in Oregon. If anybody's ever been there, you know there's lots of trees in Oregon. Our null statement is P1 equals P2. And it's actually, I'm saying P, but it's actually rho 1 equals rho 2 because it's the population parameter, where rho 1 is the true proportion of trees killed by moss in the treated area, and rho 2 is the true proportion of trees killed by moss in the untreated area. Here's our test statistic with the formula that I just gave you. Again, notice the 3 different proportions. In the first area, the proportion that were killed was 16%, so that's that one. In the second area, the proportion that was killed was 18%, so that was there. And then the global, if you add up all of them that were killed divided by all the trees tested, was 17%, and that one goes down here. Do a little math, plug it in, you get a p-value of 0.55. Obviously, with a p-value that large, we will fail to reject the null. There is not sufficient evidence to suggest that the proportion of spruce trees killed by the moth is different for these areas. Now, it is important that you're able to set up the equation just like we did in the previous chapter, but there is a button on your calculator, a test on your calculator that will allow you to test the p-value for it, and I will show you those tomorrow in class. Alright, so what I would like for you to do, we have 2 more examples here. Example 4 about teachers, and example 5 about gun control. I would like you to try and answer both of those questions, and then we will talk about them in class tomorrow. And then also example 6. So 3 examples. We're actually going to do example 5 and example 6 in class tomorrow, so you do not have to do those 2 for tonight, but I would like for you to do example 4 on your own to try that, and then we can talk about that tomorrow. Alright, so good luck, and I will see you in class tomorrow.